has calculated the index entry size in our place. How can that affect the rest of the parts of the question that provide in this one? So,
Hi, Julia. Do you remember the 10 exam?
my question is that if I calculated the data entry size in our way, how can that affect all the other parts that depend on that?
You mean what the data entry is like?
The size of the data entry. If it's calculated another way for calculating the number of leaf pages, for example, how can that affect all the other things that use this value?
Oh, you mean how can we fit if it's filled with data? Okay. That's actually the action intention of this problem is that they actually leave some of the space of the page for the metadata. So the whole 1,000 bytes are intended for the data entries. So you just divide the word value to give you the correct answer. But if the data entry, the data page, the actual size of the data page is just 1,000 bytes, then you're right. It cannot
No,
fit.
I did that.
Oh, I think that's fine. As long as you explain the things a little bit.
Okay, because the next part is asking for the height of the tree,
Yeah.
and this depends on the part above that.
Yeah.
So what is the first part is how would that affect the grading for the other parts?
Yeah. So did you assume the number?
Yes.
Oh,
I think I wrote the description of the
Yeah, I think
calculation.
that would be fine if you explain the word.
Okay, cool. Thank you.
Yeah, they're all just inside an SVG.
I was going to guilt trip you. I was like, I could self.
You are so full. No, I was in the left. So if anything thinks you guilt trip someone.
Because it's gone moving.
That makes sense. I don't know if it's that's right. So, and what if you're doing it? Yeah, we're doing deeper.
Yeah, you have a, I thought I could have looked at the
You can just things right there. And you can just write in the notebook your top. That works too.
You're much more prepared than I am.
Now, there are two classes that I take like the notes for, and then we do like the knowledge. Are you doing this in your life today?
This one. Really?
Yeah, it's
probably cost like more than like a couple bags of coffee.
Yeah, we spent $5 on it.
Well, I don't know if we talked about the things. Maybe they could do it alone. They could. I don't know. Maybe for me, it's a whole lot of practice. Everybody asked me that they would, so I usually get sick and I just pop a week after this brush.
Like, okay.
They first pay attention. Because I remember too, he doesn't like giving extra credit. At least that's what I remember. No. Did you do that?
I
Really, no.
he didn't explicitly.
I don't think we will, because I don't remember we canceled this or two.
What? I don't think he makes no.
I think that's why he was like, maybe we should do like a Skype or something. This year, as far as I know so far.
I haven't gotten any, like, because I know we
I just
haven't
remember
made
talking about it when we started meeting. I think he's what was supposed to last
That's
season.
tomorrow, and then kids, all my classes, there's work, just to get ready. So, I just wanted to know if it's not here, it's totally working.
All right, guys. Pepe is out of town today, so I'm giving this lecture instead. Just one first question. So, where did the last lecture end? Like, is that this? Did he finish the two-way merge sort with 3 buffers? Right.
I'm not sure if he finished it. I know he talked about it a little bit.
Yeah. So do I need to go through this like two-way sort with 3 buffers again, or you prefer I continue?
If you could go over it again.
Yeah, sure. Okay, so this thing have been discussed the week before the fall break. So if you are going to sort a very large amount of data with a very small memory, you need the external sorting first, right? You need to write your data into your secondary storage and utilize that to complete the sorting. So here's a extreme example that you only have 3 memory buffer pages, right? And you have like tons of data. So how are you gonna sort all the data? So I think he covered this, so I will go through this briefly. Okay. So you use one of the buffer page as the output page. That's to say, when you do the sorting, you want to output something, you put that particular tuple into that output one at a time, and whenever it's filled, you dump it to a disk. The other 2 buffer pages that's remaining are used as the input buffer pages. So when we do the merge, we basically each time would bring 2 sorted pages and merge them into the output buffer and dump it to the disk. So basically that's what this does. So for the first phase, the prepare phase is like internal sorting. Each time you bring in 3 pages and sort them in the internal memory using any of the algorithm you want, like quicksort or any sorting algorithm that's fast enough. Then you will get like multiple runs of sorted data on the disk. Each of the run will consist of up to 3 pages. Then in the subsequent phases, each time you bring one page for each of the rungs and bring in 2 rungs. And you use the merge algorithm, which basically scans through the 2 rungs, and each time you produce the smaller tuple of your head and put that into the output buffer. Then whenever the output buffer is filled, you dump that to the disk. That way you will get like larger rungs of sorted tuples, and you get fewer rungs. In the end, you will get a single rung with all sorted tuples. That's how the external sort works. Okay, so this is like the two-way sort using 3 buffers. Here's an example. So suppose each of our page contains 2 tuples. And the first yellow blocks are the input data. And in the first phase, you basically you sort them, right? You sort them in the memory. Of course, this is a bit different from what was described on the previous page. In the previous page, we said in the prepare phase, each time you use all of your available buffers to create a largest possible rungs, right? But here we only sorted like each of the block. Like for example, the second block 6.2, we bring it into the memory and sort it. It becomes 2.6, and you dump it to the disk. Then each time you bring in 2 rungs and 1 page for each rung at a time. So after the merge, after you merge the first 2 blocks, first 2 rungs, you get 2, 3, 4, 6, right? That's sorted. And you have like you bring the number of rungs from 1, 2, 3, 4, 5, 6, 7 rungs down to 4 rungs, and each of the rung will consist of up to 4 tuples. And when you continue this process, you will, in the end, after pass 3, you will get a single rung with all sorted data. Question?
So what's that black box on the right?
Oh well, that black box, right? That's a non-existent page. So sometimes you get a partial rung. Like in this example, you only have originally you only have 7 pages, right? So you don't have actually have data for the last page of the last rung. That's what the black box means. So actually, with this diagram using 4 passes, you can sort up to 8 pages. But we only have 7, so that's what it's saying. Yeah.
So would you normally too do like, so in the initial first step, like since I guess if you have like 1 megabyte RAM,
Yeah.
would you normally like go through and like sort just as an initial pass, like sort as large of chunks as you can?
That's
just
what
using-
I would do. I would sort as large as
And then using like quick sort or whatever, some efficient memory sort.
Yeah, actually, you can use quick sort. We will mention later. There's actually a better algorithm for this case. Yeah. So that algorithm doesn't necessarily have a better time complexity-ish thing, but and also it has more likely has a higher constant value. So that means with the same complexity, you have a worse running time, but actually it can produce a larger run in expectation. So that will cause you have like fewer passes, you do fewer IOs. That's the really important thing with external, the lowering the cost of external sorting. So this is it. I'll skip all of this. So in terms of the cost, all we care about in the external sorting is the I/O cost. So we basically count how many I/Os we are going to do. Like for whenever you have a pass, actually you are just scanning through all the data at once. So that's all the data pages you are going to scan through. So to calculate how many I/Os we need here, basically you need to calculate how many passes you need for this particular sorting algorithm. So the first pass is, of course, over the input data, so it's just like N over B, right? And for subsequent passes, the cost is still n over b, but you have to count how many passes you need. So that's where this log 2 n over b comes from. So basically, you are doing a two-way merge. So each time you reduce like your number of rungs by approximately half. So the height of the whole tree is log 2 n over b. Any question about this? No. So the total cost would be 2 times n over b and times the height plus 1. That's the scan of the raw data. And why there is a 2 multiply here is that is because you scan the data as input once, and you also dump them to the disk once after each pass. So that's where the 2 come from. So that's basically I think was covered in the last lecture. So that's basically the idea of two-way sorting. But typically we have more buffer pages. Like our memory could contain 1 GB of memory, so that could be several millions of pages. So how are you gonna fully utilize them wisely? So that's what we are gonna do. So for the first prepare page, we still use as many pages as possible. So here, if we the total size of our memory in bytes is m, and the size of each page is b, then we have like m over b memory buffers for pages, right? So we can bring in m over b main memory, m over b disk pages into the main memory buffer at one time, and sort them into a run and dump them into the disk. So what will that give you? That will give you, let's write it down. So suppose you have n bytes of data, and your memory size, this is the memory size, is m, and b is the number of bytes in a page. This way, how many runs are you going to end up? It's basically n over b, that's the total number of pages. And each run consists of up to m over b pages. And you take the sale of it. That's basically the number of runs in pass 0. This is the number, right? And for the subsequent, now if you look at it, you have several runs of data pages. Say we have 2 runs, no, like maybe 4. Okay, we have. So each run will have several pages. Yeah, these are all pages. This is an unoccupied page. So this is run 0 and run 1 and 2 and 3, right? And so suppose we have 4 pages in the memory. So here we will have like a memory with 4 pages, right? So what are you going to do for the merge phase? What we are going to do is that we use only one of them as the output, and use 3 of them as the input. And we merge 3 runs at a time. So that means we bring the first page of the first 3 runs into the memory first, So say this is page 0, 1, 2, 3, 4, 5, 6, 7, 11. Then we will first bring in page 0, page 4, and page 8. Then we maintain 3 pointers here. They all point to the first tuples of each of the page. Then we compare which of them is the smallest one, right? Suppose it's this one. Then we copy this tuple to here, right? Then we move the pointer to the next. And then we do a loop to continue this process until one of the pages is depleted. Say it's this one. So now your pointer fall out of the page. How do you do? What are you going to do next? Similar to what was done in the two-way sorting, right? You will bring the next page of the second round into the memory. So that will give you page 9 here. Then you reset the pointer to the beginning. Okay. And at the end of the day, you will get all the first 3 rounds in a single round with sorted order, right? So, any questions about this?
Yeah, just to be clear, so when you say like run 0, run 1, run 2, those are those the same as like input 1, input 2, like those are the same lists, or?
Not actually, so, no actually, so the input 1, 2, 3 here are the main memory buffers, right? They are input 1 is 1 page, input 2 is 1 page, right?
Yeah.
But the rounds actually consist of multiple pages.
Okay.
So what you actually do is that you bring 1 page of each one at a time into the memory, and it's in the corresponding like memory buffer location.
Okay, so the disk would just store like what the increment is between the runs, and that's why you would get the 0, 4, and 8, like the first of each of the runs?
Yeah,
Okay.
you only store the like first page of that in the
Okay.
memory. And once one is depleted, you move to the next, bring that into the memory.
Okay.
Okay, clear? Okay, so so this will give you an idea. So after the first pass, you will have 2 rounds. One with 12 pages, one with 3 pages, right? For this configuration, you have 12, 13, and 15. So this is a non-existent page, so I just mark dark here. So these 3 are merged together, so it will produce a 12-page one, and this one will retain the same. It's a 3-page one. Okay.
So I was wondering then, like, so if you're pulling in these pages and you're comparing and you're merging like 3 lists at once, wouldn't this, it seems like this would degenerate if you have like a large number of pages to merge, like, I don't know, if you have like 100 of these things and you have to look at 100 different
Yeah,
ones.
that's right. So actually, say you have like 1,000 input buffers, then you will bring in 1,000 rounds at a time, right? And each time if you scan through all the rounds, it will take a lot of time, right? That's what you are saying. So in this case, actually, we will use a heap, min-max heap, right? We can use a data structure called heap. What's a heap? It's basically a tree structure. It's defined as this. So for a heap to be a heap, first it's a binary tree, okay? And each of the node here is a number you want to compare. Say it's 4, 5, 6, 8. This is not including. I'll show this. 9, 6, 8, 10, and 12, 13. So the only requirement of a heap is that by heap I mean actually the min heap. So what it's saying is that each of the nodes in the tree has to be smaller than or equal to any of the nodes in its subtree. That still says 4 has to be smaller than or equal to all of this, and 5 has to be smaller than or equal to all of this. Okay, is that clear? But this is not actually not a binary search tree, because as you can see here, 10 is here and 9 is here. In a binary search tree, you cannot have a 10 here and 9 here because 10 is larger than 9. It has to be like visually it has to be on the right, right? But in a heap, it is allowed as long as you maintain all the requirements that the parent node is smaller than or equal to all of the nodes in its subtree. So with this data structure, it is very obvious the root is the smallest item of your concern, right? So what we are going to do here is that when we bring in the first pages of each of the run, we create a heap and insert all the first tuples into that particular heap. And each time when we want like the smallest one, we just remove the root. Okay, that will give you the smallest tuple in the head of each one. But so how to maintain a heap? To maintain a heap, when you remove this, right? So it becomes 2 trees, right? When you remove the root of a binary tree, it becomes 2 trees of forest. So this way, you will have to. A general way to do this, to maintain the property of the tree, you just replace the root with the last element. Typically this whole tree, since it is what's it called? It's not a full binary tree. I think it's called a complete binary tree. Complete binary tree. So what's this? This is like a tree that cannot have holes in it. If you, I'll first recover this. So if you put this tree in a mid-order traversal, the pre-order traversal, you will get an array, right? You will have 4, 5, 6, 10, and sorry, it should be, maybe I'm wrong, right? No, it should be a BFS, breadth-first search. You organize the tree into an array, and you lay out the tree in a breadth-first, each line will have 5. So it will be 4, and the second level 5, 9, and the third level 6, 10, 12, 13, right? This is how this tree will be organized. This is a simple array, okay? Yeah.
And I think the property right you're going for is that it has to be complete so that like all of the levels are filled except for the leaf level, right? And then I think it's the
that's right. That's what I'm going to say. You can have like this. You can have like this. This is still a complete tree, and it is actually the typical organization of a heap. But you cannot have this. Like you, for the 9, you have the right child, but not having the left child. It is not allowed, because that way, if you lay out this, you will have a hole in the whole array. Okay, so you don't want that. You want the array to be contiguous. So it's like this. But with this, there's actually some nice property you can play with. Say you remove the smallest element here, it's 4, the root, right? And you want to maintain the data structure. How do you do that? You just remove the last element and put it in the root, right? And this way you will still get a complete tree, but not necessarily a heap, because this one is actually larger than its child, right? But you can do a push down. How do I do that? You compare this with all 2 of their child, and you move the smallest one of them. First, it is larger than one of them, say 5 or 9. 3 is larger than 5, right? So this violates the property of the min heap. So you will move this down to the next level and bring one of the child to the first level. But which one? 5, right? Because you want to bring up the smaller one of them. Otherwise, it is if you bring 9 here, 9 is greater than 5. You still violate the property of the min key. So it's like this. And what is the child of 13 now? It is 6. If you look at here, it should be 6 and 10, right? And it is still larger than that. So you bring up the smaller one of them. So that's 6, and you push down the 13. And this way, if you draw it here, you will find you can easily verify that this is a valid min key. 6 and here's 13. Okay. So 5 is smaller than all of them, and 6 is smaller than all of them, and that's a leaf you don't care about. So that's still a min key. Why did I mention the array? Because in a complete binary tree, say this is the subscript of each cell. This is 0, 1, 2, 3, 4, 5. And for 0, its child will be 2 times 0 plus 1. And for this is the left child of 0. And its right child will be 2 times 0 plus 2. And this is the right child. And you can easily verify that each of them actually satisfy this relationship if you replace the 0 to the subscript I. So suppose your node is in a cell of subscript I, its left child will be 2i plus 1. And its right child will be 2i plus 2. So this way you can easily maintain this, manipulate this min key. Okay, so I don't know if you have any question about this data structure. No? So anyway, this is actually I don't know if this is required. Since Dylan mentioned this, if you have a really large memory buffer and you have a lot of ROMs, you really want to do this because each time you pop up one of the things, you only have a time complexity of O log n, where the n is the number of ROMs. But if you do a naive approach by using a loop to find the mean value of the whole all the ROMs, it's OA. So this is like much better, much smaller than OA. Okay. Just like this. So, any question about this part? No? Yeah.
Where do you store the min key? The buffer or
Oh, store the min key? Oh, yes. This is actually a good question. So, here we have a very ideal model. So, actually, you will always have some spare memory to store the min key. Okay. So, if your memory is really like n bytes in total, you don't want to use all the n bytes for the input buffer and output buffer. You will always leave something for your your database system management, like the metadata, and also like the auxiliary data structure here. Okay. So really, you are using like n minus something of the memory for the buffer pool. Okay. So I'll continue with the discussion here. Yeah. So, so in general, if we have like n pages, n bytes memory for the buffer pool, after the first pass, we have, as we mentioned before, it's n over b divided by m over b sorted rungs of pages. Sorted rungs, and each rung will have up to m over b pages. And for the subsequent passes, you will use m over b minus 1 rungs at a time and merge them into one run. So that's like, so if I have, I'll write it somewhere here. Okay. So this is like pass 0, right? If I ask you how many runs I have in pass 1, after pass 1, what is that? If I'm wondering how many runs are there in pass, after pass 1, what is the number? Can you somebody tell me? How many runs? Okay, anyway. So in the first pass, after the first the pass 0, you have this many runs, right? And in the second in the pass 1, you merge like m over b minus 1 of them at a time. So it will be divided by m over b minus 1. And you take the cell of it. That's the result, right? And as you can imagine, after pass n, you will have n over b divided by m over b. This is pass 0. And you will have m over b minus 1 to the power of, sorry, I will use n here. I will use a k. It's over the k, right? This is the total number of runs after pass k. Okay, so if we want to compute how many passes do I need, I just let this number to be 1, right? When I get only one run, a single sorted run, the whole algorithm is ended. So I want this number to be 1, and if you solve for it, it's k equal to log. You can just ignore the setting here because that's approximately it will equal to without the saving part. Okay, so it's basically log m over b minus 1 n over b divided by m. Okay, this is the total. This is like if your k equals to this number, the total number of passes including pass 0 is k plus 1. Okay, so and the merge phase will this is the total, and the merge phase will have k passes. That's the number. Okay, so if you want to compute the total number of files, that would be 2 n over b times k plus 1. This is the total number of files. Right. For each of the pass, you're reading the whole file once and the file once. That's where the 2 come from. The same as before. Okay. So any question about this part? No? Okay. So with that, I will continue to the next part. This is what I was saying. So here's a concrete example. Yeah.
Oh, I was just trying to see what you were just writing.
Oh yeah. Sorry. Yeah. So with that, actually, we can apply that calculation to a concrete example. Here we have 5 buffer pages, and the total number of pages in the file is 108 pages. So, like for the pass 0, you will use all of the 5 buffer pages to do an internal sorting on every 5 pages in the file, right? So, anyway? So, for pass 0, we will have 108 over 5 sorted rounds of pages. And each round will have 5 pages, and with the last one being only 3 pages. And in the second pass, you will use 4 of the buffer pages as the input, so you will merge 4 runs at a time, and use 1 of the buffer page as the output buffer. So that will give you 22/4 runs, right? That will give you 6, because 22/4 is 5.5, right? No, sorry, no. It's 5.04, right? Oh my gosh, arithmetic is so difficult. What this number is? This is the ceiling of 5.5. Yeah. So that will give you 6. Okay. So that's 6 runs, and each run will have 20 pages because you merge 4 runs of 5 pages each. So that will give you 20 pages of each run, and the last one will only have 8 pages, right? And for pass 2, you can merge 4 runs from the previous pass. That will give you 2 solid runs, and 1 run with 80 pages, and the other one with 28 pages. So you need the last pass that will merge the 2 solid runs from pass 2, and that will give you a solid file of 108 pages. So the total number of IOs here, what is the total number of IOs here? Can anybody give me that number? So it will be each time, for each pass, you reading the 108 pages once and write them once. So the total number would be 2 times 108, and times the total number of passes here is 4. So this is the total number of IOs.
So it ends up being 864.
Yeah. 864, that's right. Thank you, dear. Yeah. Why is external sorting very powerful? This table actually gives you an idea. So here, N over B is the number of pages in your key file, the file you want to sort. And say you have, what is this number? It's 1 billion pages. And you only have like 3 memory pages. Memory pages for buffer pool. That's if you only have 3, then you only need 30 passes. That's actually extremely fast if you think about it, because your memory is like you only have 12K memory, and you are gonna sort billions of bytes of data, and you only take 30 passes over the whole data. That's done, right? And when you increase your buffer pool size only to like, say it's just 257, you bring the number down to 4 passes. So if your memory is larger than that, you will get to lower number of passes, of course. But even if you only have a moderate size of 257 pages, if you are gonna use external sorting on a heap file with so many 1 billion pages, it only takes 4 passes over the whole data. So that's extremely fast compared to the amount of data you have. So the takeaway here is actually you might want to use you fully utilize all the buffers you have here, right? Say for pass 0, you want to generate the largest possible runs, so that you have fewer runs in the later passes. And also, it is very important to have high fan-out during merging, right? You have more memory buffer pages, you will get a higher fan-out. That will give you a shallower tree, that means fewer passes. That will lower the IO cost. Okay, so up until now, we only care about the IO, and even it is I/O, we don't differentiate between random I/O and sequential I/O, right? Because as Feifei mentioned before, in the I think it's in the storage part, for a traditional spin disk, the random I/O is like 10 times slower than sequential I/O. So here we only counted the number of I/Os here. We didn't take into consideration that we also have random I/O and sequential I/O, right? And also we also assume that the CPU cost is very small, but that is not always the case. Because if you think about it, if you have like 10,000 memory pages, and you want to sort all the data in those 10,000 pages, how many data you will have? I would assume that's like 100 million or 10 million. Even that, if you do a naive quick sort on that, it will like take at least 1 second, if I remember the time right. So the CPU cost is actually not very cheap. So it's worth reducing the cost as well. So where does the CPU cost come from? It's basically the internal sorting algorithm you use in pass 0. So for pass 0, if you only use the quick sort, it's very fast. If you do it properly, like you use randomization or you shuffle the data, you will have like a time complexity of n log n in expectation. So that's good. And in my experience, the quick sort will has a very low constant there. That means even if you compare that with the sorting algorithm with the same time complexity, it tends to be faster. Okay. But the problem of quick sort there is that if you only have M over B pages, you can only produce rounds of M over B pages each, right? Because you have bring in the whole all the pages into the memory and sort them and dump them. You do not have any other space that is available to you, right? But it really, actually, as we mentioned before, in external sorting, it is extremely important that you maximize the length of each run, so that you can reduce the initial runs you are dealing with, right? So here's an alternative to the quick sort. In this case, it's called tournament sort or heap sort. The heap sort is actually, I believe it's a bit confusing because it's like you can use a min heap for sorting. That will still require that many memory, and you will still get runs of length M over B. But actually, here in this context, heap sort refers to the tournament sort. I would prefer that name. Okay, so here's the idea. So we have a lot of memory pages, right? And we can sometimes if we can have a sorted file or almost sorted, yes.
So I was wondering, so why couldn't you do like quick sort? Because if I remember right from my data structures class, quick sort only requires like log n of extra memory just due to the stack.
Yeah.
So that doesn't seem like that's, I guess
Yeah, that's
communication.
right. You're right. You're concerning about the extra memory, right?
Yeah.
But actually, what I'm saying here is that with quick sort, you have, say you have 2 pages, right? You can only bring in 2 pages at once. Okay? So you fill this page and call quick sort, call Q sort on them, right? And you write them to the disk. Okay? So what will that get you? Say you have a lot of pages. You have 6 pages. And after this, you will have 3 runs, right? Okay, so for 3 rounds, if you still use this strategy, of course it shouldn't be 2. Actually, it should be 3. Let's make it 3. Okay. Let's make it 3. Here's 3. Okay. And if you do a subsequent merge, you can only merge 2 rounds at a time, right? And that will give you 2 passes. But what if my data is like this? My data is like, in the original data, it's separated into something like this. So it will increase first, then decrease. It's like 1, 2, 3, 4, 5. When it reaches the extreme value, you lower it down. It's like this. And you want to sort this data. So of course, if you do a sequential scan and whenever the trend changes, like it's changing from increasing to decreasing, you end that sequence as a run. So what will that give you? It will give you 2 runs, right? This is one. This is not a very good example actually. I think about it because I have to make them in the increase on the verb. I can change this to 1, 2, 3, 5, 1, 2, 3, 4, right? This is also legit, and we can have like 2 rounds if we just do a simple sequential scan, right? So this way we will actually, in the subsequent passes, we only have 1 pass on it.
So the issue with quicksort is that we don't have enough pat rounds to do it?
Yeah, actually we want to reduce the number of rounds.
Oh, okay.
To increase the size of each round. So that's where the tournament comes into the problem. So that's to say this. So this actually gives you an insight of the tournament sorting algorithm. How do you do that? So actually, this is not very good because whenever you detect, if you only use sequential scan, you are not fully utilizing your memory because you only need 1 buffer pool for your input page and 1 output buffer pool for your output, right? So how can we do that? Say I only have some small variations in my data. It's 1, 2, 3, 4, 5, 6, and say it's 5. Then it increase further. What I really want to do is that I can have like this one. 1, 2, 3, 4, 5, 6. And I have a 5 here, so I cannot input that, output that here, right, in the same round. But I can, if I can somehow remember this 5 somewhere else, like put it into the next one, and I continue with the sequence, 7, 8, 9, 10. That will actually give me a larger round, right? So that's I think that's the intuition behind this algorithm. So, but how can I do this very efficiently? So, this is how I'm gonna do it. So, I have a memory, right? And as I mentioned before, the heap, we are going to use a min heap here. Okay, and as I mentioned before, the min heap can be implemented as an array. And if your min heap has n elements, you only need n cells in the array, right? So if you treat all of your memory as a large array, say it's like this. This is the I think you will also need the output buffer, and the input buffer. That's 2 reserved pages. And for, say you have M over B pages, you just leave 2 of them, one as the input, one as the output. And the remaining of them are used as the bin heap. So conceptually, you maintain 2 heaps. One is initially one of them, H1 is full. So say H1's for the first heap, your index starts at 0 here, and it goes all the way down to say it's some number. Okay, it's N1. Okay, so this is H1. So where is H2? It's actually here. It's H2 is a zero size mean key. So this is how the configuration initially look like. So initially you bring in like as many data as possible, and you insert them all into the first heap, the H1 heap, and you make the second heap as a zero size one. Okay, and now since your memory is full, you can bring in another page, the next page here, right? You can bring in this page here, and you look at the first tuple. So let's skip this for now. We will look at the first heap here, H1. So for H1, you know the root of the H1 is the smallest item in there, right? So you can put this to the output buffer, put this to the output buffer, right? And you can pop one element from here. And then what you are going to do is that you need to reorganize the min heap H1. So you move the last element here and somehow do some push down and push ups, right? Then you will have an empty slot here. For this empty slot, actually you have two choices. You can actually use this for H1. That means you will insert one more element into H1. Or what you can do is that you can use this slot for H2. You can make H2 a min heap of size 1, right? So so what you are going to do is that, say this tuple is, let's use the same notation here. So say the element you remove from H1 is n, okay? The key of it is n. And you look at the first tuple in the input buffer is R. And you can think about our analogy before. If since m is already in the output buffer, you cannot output anything smaller than m into the output buffer anymore. Otherwise, the current run is not sorted, right? So you will require if R is to be inserted after n in the same run, it has to be n smaller than or equal to R, right? Any question about this? If you want the next tuple in the input buffer to be inserted after n in the same run, it has to be greater than or equal to n, right? Because the same run has to be sorted. Okay. Then what if this doesn't hold? That means n is greater than r. Then you put this number actually into the next one. So that's where the H2 comes in handy, right? Because this run actually doesn't serve the current run. The current run only gets data from H1. So you can put the R into the H2 min heap here, right? And this way, you can still fully occupy the memory, and still you don't violate the property of the whole run. That means it's gotta be stored. Okay. That's what the algorithm is saying. And once you depleted H1 at some point, now the whole memory is H2, and your H1 is here, H1 with size 0. You finish the current run and you start a new run, and make H2 the H1. Is that clear or is it confusing? Yeah.
Okay, so H1 is like the current round, and then if you run into anything that you can't output, then
you put that into H2.
Okay.
Okay.
All right.
Yeah. And so H2 will be used for the next run, so it won't affect the current run to be sorted, right? the current run is always sorted because you always extract numbers from H1 and you don't insert anything that's smaller than the largest you have put into the output buffer.
Okay, so I do have a question. In this code,
Yeah.
you remove M from H1, but then like it doesn't looks like you don't ever like reinsert it. How do we know that it's been like how does M get output then?
Oh, well, actually this is, I think, no, there's another sentence here.
Oh,
Containing the output buffer, right?
Okay.
So whenever you put, you remove one element from H1, you put that into the output buffer.
Okay.
And the key point here is that you always replenish the one of the heap when you remove one element from H1. You move the next tuple in the input into H1 or either H1 or H2.
Okay.
So that your H1, the size of H1 plus the size of H2 is always all the memory you have.
Okay.
Okay? Yeah. And that's doable because the heap can be organized as an array. That's actually doable. So basically, this is the algorithm.
And then so what's the advantage of this one over like what we talked about before about just using a heap?
Yeah, so if you just use a heap, the heap can, like, you still can only use up to M over B buffer pages, right? You can use you can use all of your M over B buffer pages as a heap and try to insert stuff into it. And each time you remove an element from the root and insert that into the output buffer and dump that to the disk, right?
Yeah.
Yeah, so that way it will give you a run of length up to M over B minus 1, right? But with this, if you think about this, if your data is fully sorted, actually this is what we are going to talk about. This actually, what's the best case of this? If your data is fully sorted, actually you will get a run of the length of your whole data, right? Because each time when you get a new element, it's going to be larger than the element you removed from H1. So it's always going to be inserted into H1. So that way, your H2 is always empty until you depleted all the input data, right? So that's the best case scenario. If your data is sorted itself, it will give you a run of length the whole file, right? Then your algorithm finishes. But what's the worst case? So the worst case, your data is fully in the reverse order. Each time you get a new element, it's going to be inserted into H2. So you can only get a run of length M over B minus 2, the size of your heap space, right? So, but that's still actually match. That's the best case of quicksort or naive heap sort, right? Because for naive heap sort or quicksort, you can only have a run size of, you can always only have a run size of up to M over B minus 1. But this way you are just losing one page at most, right? And on average, the average case is actually 2 times M over B minus 2. This explanation is actually, I don't know if you can understand it. At least I find this really informal. It's like, if you think of a snowplow, so it's moving around a circular track, and it's removing the snow, right? So if you think about it, it's like if you have a plow here, right, and you have a circular track. So the amount of snow here is actually 0. You don't have snow here because it's removed, but you have a lot of snow here behind it, right? So if you cut the track and expand it into a line and plot the amount of snow as a triangle, against the track, it looks like this. this is actually behind the snowplow, and this is just in front of the snowplow, right? So every time you move ahead, the snow is still accumulating on the track. So each time you move ahead, it's in a steady state. So that means when you move here, actually not. Should be like if your snowplow is here, and you move ahead a little bit, so your snow is the snow in front of the car is still zero, but here the snow is gonna be filled to the same height of this. So it's like this, right? When you move forward a little bit. So if you think about when you complete a circle here, complete a full circle here, and you imagine you pull somehow, since this is circular, so you can bring this back to this point, and you can think about how many memory, not memory, how much snow you have removed. That's like, these are the original amount that was on the track when the snowplow was at this point. And this upper triangle is the amount of snow that was accumulated during the whole run of the track, during the process. So this way you can think the whole amount of snow that was removed is actually 2 times of the lower triangle. But what is the lower triangle? It's actually it's in this analogy, it's the memory size. So it's like this. So that will give you an idea of why they say this is an analogy of the average length of the rock. But do you think this is understandable? No, I'll show you. Actually, when I first saw this, I couldn't understand, and I searched on the internet. There's a Google group here, actually discuss about this. It's called snowplow analogy, something like this, and it's a question from, it's the first in a row. And if you wonder about it, you can take a look at this particular thread here. I was just describing what was said here, but actually I don't think this is a very formal proof. Here it gives you a reference to the formal proof. It's in Knuth's Art of Computer Programming Volume 3, Sorting and Searching. I think this algorithm also comes from there, and you can, if you are interested actually, you can take a look at the proof. But the whole point here is just the whole point here is just the average length is actually longer than the best case of your quicksort or heap sort. So you have a larger run length, so that will give you fewer passes. Yeah.
Why is the average length of a run is you minus 2 there?
Oh, you mean the minus 2? Oh, yeah, because in this algorithm, you have to reserve a page for the output buffer and reserve a page for the input buffer. So that's where the minus 2 comes from. Okay.
But you mean the other 2 page is H1 and the first 2 page?
No, actually the H1 and H2 actually occupy B minus 2 pages or M over B minus 2 pages. Okay, and the remaining 2 pages, one is for the output. When you remove one element from H1, you put that into the output buffer, right? And whenever the output buffer is filled, you dump that to the disk. So you need that page. And also you need a page for the inputs. So to bring in new tuples from your file, you need a buffer pool for your next page in your heap file. Okay, so that's where the 2 pages are useful. Okay, and for H1 and H2, you can use as many memory as possible. That's all the remaining pages, that's O will be -2. And in the analogy here, actually the snow on the track initially was the size of H1 plus H2. Okay, so that's N will be -2. Is that clear? Okay. Yeah. So this is the tournament sort. I'm sorry if you find this a bit confusing. You can look at the illustration here and also look at the pseudocode. Hopefully, you can understand the whole idea. The idea is basically you want to produce a larger work so that you have fewer passes on the whole data. Okay, so finally, there's two other things for external sorting. So that's remember when we do I/O on the disk file, we have a blocked operation. That means when you read the data, it takes quite an amount of time, like several milliseconds. In several milliseconds, you can actually do a lot of CPU work. But when you bring in a new page or when you are dumping a new page, if you are using a synchronous write or read, it will block all your operation for a few milliseconds. That's a lot. Okay, so we have many other considerations for this. So actually, we use asynchronous read and write, right? But that will mean we need more blocks for our prefetch or asynchronous write. Because when you do an asynchronous read, you have to provide a target array. It cannot be the current buffer pool you are using because otherwise in the process it's gonna get overwritten, right? So the idea here is that you use 2 pages for each of them. One of the page is actually the page you are looking at, but the other one is the next page you are gonna do a background read that is prefetched into the memory. For example, here we have N over B memory here, and we use 2 pages for each of them, and 2 pages for the output. So here's what we are going to do. Like when you are scanning through input 1 to input K, you are looking at the yellow ones. And once let's say the input K is depleted, and you need data from the next page in the same run, right? You will directly look at the input K prime here. But this is actually done in the background. Like during the process you are scanning through the K, you already prefetched the next page into input K prime. So that you can just switch this color to yellow and switch this color to black. No, it's not black, it's blue. Okay. And you once you complete this switch, you do another prefetch of the next page that's also in the background, and you can continue with all your scanning operation. So that's the double buffering, what the double buffering do. So we also need a double buffer for output, because once we fill up the output page here, we need to dump it to the disk. We also want to do that in the background. So you also need a second page for you to produce more outputs, so that the writing process doesn't block other operations. Okay. So this is like the double buffering. So with double buffering, of course, you are getting more runs because you have fewer memory for the runs, right? So say we have we have 10 buffer pools, and we have 1 page input and output buffer. That's the original algorithm we discussed. That's like we have 9 runs at a time, right? We merge every 9 runs into 1 run. So that will give you actually fewer passes. But if we do a double buffering, like we have 2 pages for each of the input one and 2 pages for the output buffer, we end up with 4 runs at a time. We merge every 4 runs into the run. So that will give you more passes, but you actually overlap your CPU time and I/O time. So that's actually depending on the real scenario, it's typically better than the one-page alternative. Okay. But this is actually not absolute because sometimes you can do like 3-page input or output buffer. That depends how fast is your disk and how fast is your CPU. I think the general sum is, rule of thumb is that you don't let your CPU wait for I/O. If you have a slow I/O, then you will want more buffers for each of them, so that you can always continue to the next page when you have depleted, finished scanning one page. And you overlap all the I/Os for the next pages with your CPU cost. Okay. And yeah, and the final part of this is that, remember we have B-tree indexes, and B-tree indexes are essentially sorted file, right? Because in the leaf level, everything is sorted, right? According to some key. So we can also use B-tree for sorting, but it doesn't make sense for all scenarios. Like say we have two possible scenarios. The first one is that the B plus tree is actually a cluster. The cluster means the order in the leaf, the data entries in the leaf level is actually in the same order as the heap file, right? The data entries in the leaf level are in the same order as the heap files. Okay. If I draw a picture, it's like you have a tree here. And this is the leaf level, and this is like a sorted, right? For a B tree, this is a sorted, and they will point to some tuples in the heap file. And a cluster index means that the actual tuples in the heap file is also sorted in the same order. Okay, so then for this case, it's actually a very good idea because if you scan through the data entries in the leaf level, you can just fetch tuples in the heap file, and that will incur only one I/O for each of the page because you know that will be in order, right? Usually in a real database system, this is done by the buffer manager. So actually, why is that one I/O for each of the page? Because when you go from, say, the first link here, go to the actual heap page here, the first heap page. You fetch the first tuple and you somehow unpin it. So essentially return the memory back to the buffer manager. You say you don't want it anymore. But when you go to the second link, you go to the same page, right? And if you go to the same page, it's very likely that the buffer manager is actually has that same page in the buffer pool, right? So that way you only have one I/O per data page. But actually, for a more naive database system, you might want to use like you keep one data page at one time, and until you know you will not go back to this page, you keep that page in your memory. That's basically what this is saying. So this is actually a very good idea because you are essentially doing sequential I/O, so that's very cheap. Okay, but for unclustered index, it might be a very bad idea because you know your IOs, no, your data entry, the RIDs in the data entry can be scattered around the whole heap file. So this way, you need to really do one I/O per fetch of the tuple. Say you end up with the first page first for the first tuple, then first page for the first, then the fourth page for the second tuple. So you really need to do fetch, a data page read for each of the actual tuple, for fetching each of the tuple, right? So this is really bad because first, you do one I/O per fetch, right? This is much slower than the previous one, the classical one. The second, this is a random I/O. It is still slower, 10 times slower than the previous one, because random I/O thing. You have the disk, you have to have your the spin head to spin to the right place. That will take time. So this is generally, if you have an unclassed D3 index, you don't want to use that for sorting. So in summary, external sorting, of course, is very important in DBMS, as Feifei will mention in the next a few lectures. When you do a lot of things like query evaluation, or by or distinct, or you just have an order by clause in your SQL query, you need sorting, right? It's very important. So DBMS may dictate, may have dedicated parts of buffer pool for sorting only. Okay, external sorting. The goal of the external sorting is to minimize the disk I/O, right? So you will consider for pass 0, basically you are going to use the tolerance sorting. Because it will give you larger runs and give you fewer runs in the subsequent passes you need to merge. That will let you scan fewer passes of data. That means fewer I/Os. And also, larger block sizes will mean lower I/O count per page. Why is that? Yeah, so larger block size, actually you are looking at fewer runs, so actually you are going to have fewer passes, less of course. Right? Yeah.
So I was wondering, because most of these algorithms that we've gone over, it seems like it assumes that you have like space on your disk that have both like input and output, so you have at least twice the input of disk space. What about, I guess, the case in which you only have maybe just about like, I don't know, you're sorting like your entire memory space and you just have your...
If that's just the entire memory space, that won't be a problem actually, because that's not large, right?
I mean that like your data, it occupies like the full disk, so there's no extra disk space, but you have some external memory that you
I don't think that in that case no database can do anything useful. Right? You have already used up all your disk right? And you don't have any spare space to dump your data. So that way.
But I mean, you're sorting it in. I guess like the assumption is you're sorting it in place. Like, can you modify some of these algorithms to work with that?
No, I don't think for them they can be modified to be in place. Actually, in-place sorting, I don't think is meaningful for spin disk, because the I/Os are really, really expensive. If you do if you think about it, all of our internal sorting algorithm, most of them are in place, right? But you cannot use them because they use a lot of random access to them. That is really, really the last thing you want to do to a disk, right? So I don't think there's in-place algorithm you want to use for this particular case. Maybe something like the radix sorting, it's also in place, right? The radix sorting is in place, right? Maybe, yeah. If I remember it right, it's in place, but I don't know if there's a variation for the disk. It also assumes that it's in memory, and you also have need to have a bound of your data. It assumes your data has a bounded number of bits. That's basically I think it's a radix sorting. If you are interested, you can look at that. I don't know if there's any variation for the disk for that. Yeah, so this is basically what we talked about in this lecture and the previous lecture. And the final takeaway message is that in practice, the number of passes is rarely more than 2 or 3. So basically, sorting is not as expensive you might think of for databases. Okay, so that concludes this lecture. Yeah, okay. So see you next week.
Yes,